Today we're going to do the definition of the derivative. So you have your quizzes due tonight. D2L quiz number 2, handwritten quiz number 2, both due tonight. And we're going to do the definition of the derivative at a point today. We added this new piece to the notes that tells you which infinity questions should correspond to what we did on the notes every day. So hopefully that's a good addition. Yes, sir.
I have a question on the quiz. There was like this one question, I think that answer choices were misworded really weirdly.
So send me an email or show me right after class and I'll look at that. Yeah. Okay, so we're going to do the derivative at a point. So today begins our sort of, main idea of calculus, the derivative. And when you think about the derivative, it tells you how fast something changes. That's what the derivative does. It tells you how fast something changes at an instant. So it tells you at one very instant how fast something's changing. And so what we did in the last 2 weeks is we talked about average rates of change. We used average rates of change over smaller and smaller intervals to estimate instantaneous rates of change, right? We used average velocities, got the interval smaller to get an instantaneous velocity. And so what we're going to do now is talk about, that's the definition of the derivative at a point, how fast something changes. So the slope of the tangent line is a limit, that's why we spent 2 weeks on limits, of the slopes of the secant lines. So the average rate of change on the interval a to x is the slope of the corresponding secant line. So if you imagine you have some sort of function and you have a point A and you have a point X, then the average rate of change from A to X is the slope of that secant line. How do you find the slope of that secant line? Call your function f. How do you find the slope of the secant line? Change in?
Adjacent over hypotenuse.
No, or that's a secant function. Yeah, no, this is the secant line. Change in y over change in x. So the x values are a and x. So my denominator is going to look like x minus a. And the y values, how do you get the y values if you know the x values? Plug them into the function, yeah? So f of x minus f of a. If I want to find how fast this function is changing right at the point A, what I want to do is make that x value that I'm using get closer and closer to A, right? I want to take the limit as x approaches A of this piece, and that will give me the instantaneous rate of change. So in this case, I'm going to take the limit as x approaches A of this function, f of x minus f of a over x minus a. And this will tell me how fast it's changing at the instant when x equals a. That's one way to do the instantaneous rate of change, which is going to be known as the derivative at a point. The other way, so here I had 2 different points, a and x. They were some distance apart, which we didn't talk about. We just said let x get closer to a. The other way I can do it is I can use 2 points a and a plus h, where h is just a little bit that I'm adding to a. So remember when we were finding the instantaneous rate of change at 1, we did like 1.01, 1.001, 1.0001. So that h, that value that I was adding to 1 every time, got smaller and smaller and smaller. And so in this case, the picture is going to look pretty much the same, except I'm going to label them a and a plus h. But I'm still going to find the slope in the same way. It's going to be, what do I get when I do a plus h minus a? If I do this x value minus that x value, a plus h minus a, what do you get? Yeah, you just get h, right? And then the numerator is going to be f of a plus h minus f of a, because the slope is going to be change in y. Find the y values, you plug them into the function, over change in x. When I do a plus h minus a, the a's are going to cancel. I'm going to be left with just an h there. That's going to be the slope of that secant line joining these 2 points, the slope of that secant line. If I want the slope of the tangent line, I'm going to take this point here and move closer and closer to A. As this point gets closer and closer to A, what happens to this value of H? Gets smaller and smaller, closer to 0. So as this point, A plus H, gets closer to A, this value of H goes to 0. So instead of taking a limit as X approaches A, I'm going to take the limit as H approaches 0 of this expression. So these are two different ways to compute the instantaneous rate of change of a function f at a point A. Two different ways. They both have their pluses and they both have their minuses. Okay, we're going to practice with both of them and see how it goes. In the end, if you want to pick just one, it needs to be this one, because that's the only one that will work for us on Wednesday. But, you know, you can use either. Okay, the slope of the tangent line is called the derivative. So here we have defined it. The slope of the tangent line, either of these limits, is called the derivative. So finding the derivative at a specific x value, x equals c. This is the notation f prime. We call it a prime, f with that little apostrophe c. And there's two ways to do it. We can use either of those formulas up there. Both of them involve a limit. In this one, we could do limit as x approaches c, f of x minus f of c over x minus c. Or we can do the limit as h approaches 0, f of c plus h minus f of c all over h. In this case, that c is sort of the a value we were using above. So these are two ways to find the derivative at a particular point. So we're going to be given a number for c. It's going to say estimate the slope of the or find the slope of the tangent line at x equals 7. You're going to use c to be 7 in both of these formulas. Okay. In this formula, x is changing. X is approaching c. In this formula, h is changing. H is approaching 0. Both formulas are fine. You can pick. Okay, so here are some pieces, and they say identify the original function f of x and what value of c you're using to evaluate f prime of c. So what I want you to think about in each of these examples is where are you estimating where are you finding the instantaneous rate of change? Which c value are you finding the derivative at? What is your function? And which definition are you using? So maybe that's the easy part, right? If you look at these two things, which definition are you using in each piece? Should be easy to tell. How do you know? Yeah. One's got an H in it. So this is the one with the H. And one's got a number down here, right? So that's the one with the number. So let me write those down there, and then we can play a matching game. I'm just copying these from above. Okay, so I want to know what's my function and what's my c where I'm finding the derivative at. So in each of these questions, you're trying to figure out what's your function f of x and what's your c where you're finding the derivative at. In this one, it's easy to, in your number 2, it's easy to find out what c is, right? What's c in number 2? 7, because it says the limit as x approaches 7. 7 is my fixed point. I'm taking my limit as I get closer and closer to 7 of this slope. So in this case, c is going to be 7. What's my function in this case? Which one of these pieces represents my function? That first piece in the numerator, right? This piece right here matches. You see that? So in this case, my function is going to be 1 over square root of x squared minus 2x. So this limit, yes. We're just matching, yeah. We're just matching, that's all. Yep, we're just, these are the pieces of the definition, and we're just matching them to this expression that we have up here. Yeah, so we picked the C because we knew that this 7 here was this C. So then that 7 should appear in a number of places. It appears inside of here. If I plug 7 in here, 7 squared minus 2 times 7 hopefully gives me 35. It does. 49 minus 2 times 7. 49 minus 14 makes 35. But I was just matching to see what that C is. Okay, can you match in this one? What's C going to be in this one? And what's your F? This one's a little bit harder, I think. Look at this. Here's C here in 2 places. What'd you say? Somebody said it back there. C is 2. Tatiana says C. You guys move chairs on me today. Everybody's in a different spot. In this case, that C appears 2 places right there. C is going to be 2. You see that C appearing in 2 places? It appears with the plus H, and it appears in that second function plugged in there. C is 2. Okay, what's your function in this case? 3 natural log of x. Yeah, your function in this case is 3 natural log of x. Basically, if you think about this guy right here, 3 natural log of 2, C is 2. So you plugged 2 in there for x. So this function is going to be 3 natural log of 2. Now notice these questions did not ask you to evaluate these limits at all, right? Like we haven't practiced evaluating these limits. We're just saying, here they are. Can you match them to the definitions? What we're going to spend the most of the rest of the day on is, can we evaluate these limits? Because they're not easy, okay? Okay, so let's try one. This guy says, find f prime of 2 if f of x equals 2x squared plus 1. So find f prime of negative 2, sorry, find f prime of negative 2 if f of x is 2x squared plus 1. Okay, so what's your C in this case? Negative 2. It's the thing you're plugging in there to your derivative, okay? And we can use either definition. We can use the x minus c definition, or we can use the h definition. Doesn't matter. Use either one. I'm going to use the x minus c definition. Yeah. Okay, so f, I'm just writing it down. Limit as x approaches c, f of x minus f of c over x minus c. Okay, so f prime of negative 2 is going to be limit as x approaches what? Negative 2 of a big old fraction. I'm going to do the denominator first because it's easier. I'm just plugging negative 2 in there for c. And in the numerator, I need f of x, which is this guy, 2x squared plus 1, minus f of c. Over here, I'm going to do f of c. Negative 2 squared is 4, times 2 is 8, plus 1 is 9. So I'm going to put 9 in here. So I sort of took a detour over there, and I did f of c like over here on the side. Over there. Okay. And I put him in here. So I took a detour to do f of c. Because I don't want to make any errors, like when I'm computing this and then they get, expanded on in there. Okay, I'm going to do some simplifying. This is where the algebra comes in. Limit as x approaches negative 2. X minus negative 2 is the same as x plus 2. And then the numerator, I have 2x squared plus 1 minus 9 makes minus 8. Remember from the first week of class, how do we evaluate a limit? What's the first thing we should try when we evaluate a limit? Plug in the number. Okay, when I plug negative 2 into this function, what happens? I get 0 on the bottom and I get 0 on the top. If you have 0 on the bottom and 0 on the top, what should you try to do? There were 3 things you could try. Remember what they were? Factor, good. Combine fractions, good. and rationalize. Which one should I do here? Factor. I'm going to try to factor this guy. Okay, I'm going to factor a 2 out of the numerator. That makes x squared minus 4. And then I can factor x squared minus 4 into x minus 2x plus 2. Which is lovely because now these x plus 2's cancel. And so I have 2 times x minus 2. Rationalizing usually has square roots in it, and factoring is usually polynomials. Yeah. Okay, what should I try now? Plug in the number again. Yeah, okay, great. Let's plug that number in again. 2 times negative 2 minus 2. Negative 2 minus 2 is negative 4 times 2 is negative 8. So what we're saying is that given this function, 2x squared plus 1, the slope of the tangent line at x equals negative 2 is negative 8. If I graph this function, 2x squared plus 1, and I look at what's happening at negative 2, it should be going down. How do I know it's going down? Slope is negative. It should be going down pretty fast, right? Like negative 8 is a pretty steep slope. So if I graph this function 2x squared plus 1, and I look at it at x equals negative 2, it should be going down pretty fast. Let's try it. Okay, I'm going to graph the function 2x squared plus 1. And I'm looking at negative 2. Here's negative 2. Remember, I'm not looking at the point there, right? I'm looking at the slope of the tangent line. So if I graph the line with slope negative 8, it doesn't go through there, but you can see how it's going down. Like if I zoom in right there, you see how right here at negative 2 and that blue line have about the same slope. Yeah. So it's going down pretty fast at negative 2. I don't know whether I want to use the other definition or not. Maybe. Let's see how it goes. Okay, let's try again. This guy says, given this function, f of x equals x cubed minus 3x, and f prime of x, oh, they're giving you the derivative of this function. F prime of x equals 3x squared plus 3 over x squared. Find the equation of the tangent line. So I want the equation of the tangent line at x equals 2. Find the equation of the tangent line at x equals 2. How do you find the equation of a line? Okay, y equals mx plus b, sure. Y equals mx plus b. What does m represent? M is the slope, so I need the slope of the tangent line. Hey, what did we just learn is the same as the slope of the tangent line? The derivative, yeah, at that point, right up here. There's my important fact of the day. The slope of the tangent line for the function f is called the derivative of f at that point A. Okay, I need the slope of the tangent line. To find the slope of the tangent line, I'm going to do the derivative at that point, x equals 2. Yeah? Okay, here's my function for the derivative. F prime of x is this guy. If I want to find the slope, I'm going to find f prime of 2, or 3 times 2 squared plus 3 over 2 squared. 12 plus 3/4 is 51 over 4. What do you think? You can put that in your calculator if you want to. So the slope of the tangent line, I used that derivative that they gave me. I didn't have to do any computation this time, right? I didn't have to do that limit or anything. And the slope is 51 over 4. Okay, I'm trying to find the equation of the tangent line. So I know the slope. Check. 51 over 4. Now what? I need a b. Yep. Okay, I would like to put it into y equals mx plus b format. How am I going to find b? You want to use point slope? Sure, we could do that. So this is slope intercept. I could also use point slope. Y minus y1 is m times x minus x1. I still don't think I have enough information to use that yet, though. Because I just have this x value out here, right? What am I missing? Yeah, excellent plan. Let's plug the x value into the original function, right? If you plug the x value into the original function, then you get the y value that corresponds to that, right? So if you take the x value, you plug it in the original function, it's going to give you the y value. So I'm going to plug the x into the original function, and f of 2 is going to be 2 cubed minus 3 over 2. 8 minus 3 halves, 13 halves. So that tells me that my point is 2 comma 13 halves. And my slope is 51 over 4. I can use either of these two formulas to find the equation of the line. I don't care which one you use. I don't care whether you use y equals mx plus b. I don't care whether you use point slope. Both of these formulas will find you the equation of a line. I tend to use y minus y1 is m times x minus x1, but you pick your favorite. 51 over 4x minus 51 over 2. Add 13 halves to both sides. 51 and 13 makes 38. So $19. I mean, sometimes in your homework and stuff, you can leave it, like, I don't care if you simplify past this point up here, like this right here. You can leave it like that for me if you want to. If the homework says y equals, then you have to get it to this form, right? But if you can put in an equation, you can type it in like that and it'll check and make sure it's right. Okay, so what does this mean? If I go back up here to this thing, what does this mean? It means that if I graph that function, x cubed minus 3 over x, and I graph that line that I just found, that they should touch at x equals 2, and they should be traveling in exactly the same direction. Yeah. If I graph this function, x cubed minus 3 over x, and I graph that line that I just found, then if it's an equation of the tangent line, it should touch that function at the point 2 and be traveling in the same direction. Let's see. Okay, I'm going to go to x equals 2. X equals 2 is like right here, right there at x equals 2. The green line is the function, and the purple line, Do you see how it's touching? If we zoom in there, let's zoom in a little bit more. It's like at 2 and 6.5. There, right there. It's the purple line is really hard to see because it goes exactly with it at that point. There's the purple line. At x equals 2, the purple line and the green line are touching each other and they're moving in exactly the same direction. So the purple line is the tangent line to x cubed minus 3 over x at x equals 2. Okay. This guy says, find the slope of the secant line PQ for each point Q with the x value given in the table. Then use the answers to estimate the value of the slope of the tangent line at P. I think that maybe this P0 negative 1 was not in your, if you printed it, add that in. P0 comma negative 1. Okay, so this one wants us to go back to that estimating, right? But it doesn't want us to just plug these numbers into the function. Yeah. It wants the slope of the line that joins this point, 0, negative 1, with this point, 0.1 comma something. Okay, so it doesn't just want the value of the function at 0. We know what the limit is at 0. We know that the limit at 0 is going to be negative 1. We just plug 0 in there, it's going to spit out to us negative 1. What it wants is the slope of those secant lines joining this point 0, 1 with this x value. And then this point 0, 1 with this x value. Because what it wants us to do is estimate the slope of the tangent line at that point of that function. So let's see if we can do this in Desmos. I'm going to put that function in. I'm going to start by putting that function in. F of x is, I don't know that function now, x plus 1 over x squared minus 1. Okay, so we're talking about right here at 0, negative 1. What we're trying to do is estimate the slope of the tangent line here at 0, negative 1. It looks like it's going to be negative 1. Right? It looks like the answer is going to be negative 1. If I was going to draw a tangent line here, if I draw that tangent line in there, it looks like it has a slope of negative 1. It goes down 1 over 1, down 1 over 1. Yeah, agreed? But what I'm going to do is I'm going to estimate the slope using points that are close to it. So I'm going to use 0.1. This is my y value. So x is 0.1, y is negative 0.11. To find the slope, I do change in y, negative, let's do f of 0.1, minus f of 0, because those are my x values, over 0.1 minus 0. That gives me my negative 1.11111. So let's talk about what we did there. I'm doing this first piece right here. So what I did to get this first piece right here was I found f of 0.1 by plugging it into this function. And I got negative 1.111111. To estimate the slope between this point and this point, I did change in y, f of 0.1 minus f of 0. Over change in x, 0.1 minus 0. And that ended up with negative 1.11111. If I want to do the next value, so that was this value right here. If I want to do the next value, this 0.01, I would do the same kind of calculation. I would do 0.01 plus 1 over 0.01 squared minus 1. It would give me some number. And then I would find the slope by doing f of 0.01 minus f of 0 over 0.01 minus 0. And I would get this value here. So I did this, plugging it in. I don't know this number, but I'm going to figure it out. Okay, so I'm going to go back to my Desmos and I'm going to change the 0.01s, the 0.1s that I did before into 0.01s. Okay, so I'm going to go back to Desmos and I'm going to change the 0.1s here and here into 0.01s. And I get negative point, oh, I gotta do it down here too. Negative 1.010101, okay? So that's my next slope in the table. Remember, we were estimating and it looked like it's weird that they're coming out to be the same number. That it won't always be the case. I'm gonna do it again for this one, right? I'm just gonna change all those 0.01s to 0.001s. I'm gonna do the same thing for this side. I'm just gonna change them to negative 0.01s. And I get closer to -1. Yeah, I don't know how many decimals they're gonna make me keep, but I get closer to -1. Now I'm going to do negatives. So I'm going to make this guy negative instead of positive. And I get negative 0.999. That was this one down here. We'll do the same thing for that guy. Negative 0.99. So farther away, but we know that because we're farther from the number. And then same thing for the next one. It's probably going to be negative point something, 99999. Negative 0.9090. Oh gosh. So these slopes that are the things that I care about. That's the tricky part, is that I don't care about these values. I care about these slopes. These slopes, as x approaches 0, so I'm approaching 0 from both sides. These numbers here that I'm using to calculate my slope are getting closer and closer to 0. What's happening to the slopes? Yeah, the slopes are getting closer to -1. So we would say the slopes are approaching -1. So the slope of that tangent line is going to be -1. We just got lucky that these numbers were the same as what you got when you plugged them in. Don't think that that's always going to happen. You're doing your homework, it's not always going to happen. Yes, sir.
So like 2 plus 1 plus 0. What is it? 0.1 plus 1.
That's should be minus. Oh, it's minus -1. Yeah, because those are the y values. This y value was -1. So it's changing y. Oh, no. I'm just evaluating the function. Yeah, I was just evaluating the function to get the y values so that I could plug them into this slope equation. But in reality, Desmos did all the work for me, right? I didn't do any other work. But what you want to think about is that what you're plugging into Desmos is this slope. Like you don't even need to see this number. You could do this whole problem without ever seeing this number. If we changed this and did this at x equals -5, right? If I wanted this to do this at x equals -5, then I would change this to -5, change this to -5, and make these values surround -5. So if you were surrounding -5, what numbers would you use for those other x values? -5.1, -4.9, right? You would use those kinds of numbers in there.
This is basically doing what the derivative does, right?
This is doing what the derivative does, yeah. We're not going to take the derivative of that for like another week and a half. Yeah, because this is hard to use that formula. You can imagine if I tried to plug into that formula, a plus h minus a over h, that's going to be really hard, right? There's going to be like fractions we have to combine, a ton of factoring we have to do. It's going to suck, and we don't want to do that. We're going to learn some rules next week that make derivatives easier, but right now that derivative is not easy. We're going to do easy ones. That's how we're going to start. Okay, I want to do one where we use the other formula. So up here we did the f of x minus f of c formula, and I want to use the other formula. So insert, let's see if I can do it. Let's go right up. Here we go. Estimate the slope of the tangent line to f of x equals square root of 3x plus 1 at x equals 1. So estimate the slope of the tangent line to f of x equals square root 3x plus 1 at x equals 1. I'm going to start just by graphing this function. It's not necessary to graph that function, but I'm going to start by graphing the function to see what it looks like at x equals 1. Do I expect my answer to be a positive number, a negative number? Do I expect it to be a big number or a small number? So I'm going to begin by graphing that function 3x plus 1 and look at what happens near x equals 1. Square root 3x plus 1. So this is a graph of the function square root 3x plus 1, and I'm trying to see what's happening near 1. Let me make it flatter. I'm trying to see what's happening near this point 1. What kind of number do you think you should get out for the slope of that tangent line near x equals 1? A positive number, a big number, small number. I mean, kind of pretty much close to 1, right? Like it looks like it's pretty exactly diagonal. If you draw that slope of the tangent line in there, it looks pretty close to being diagonal. It's not, it's hard because it doesn't really go through any good points, but if I was guessing, this is a nice point and this is a nice point. So maybe it's like 2. Not quite 2 though, because it goes up 2 over 2.5. So up 2 over 2.5. So what's 2 divided by 2.5? What's 2 divided by 2? I don't know. Can't do it. 2 divided by 5/2 is 4/5. 0.8. So maybe we're going to get a slope of about 0.8. Okay, that's what we think we're going to get. So we're going to try it, and we're going to use the f of x plus h, or the f of c plus h formula. Okay, so we're going to try to find the slope exactly. We tried to estimate. We think it's around 0.8. My drawing could be really bad, so it could be really wrong. But we're going to try to estimate using that f prime of c is limit as h goes to 0, f of c plus h minus f of c all divided by h. Okay, that's the one we're going to try. Okay, what's c in this case? C is 1. Yep, c is 1. C is 1. So let's rewrite it. F prime of 1 is going to be limit as h goes to 0, f of 1 plus h minus f of 1 divided by h. Okay, over here on the side, I'm going to compute these two pieces. I'm going to see what f of 1 plus h is, and I'm going to see what f of 1 is. I like to do that on the side so that I don't make an error in trying to do it in here. Because this minus sign is going to get people every time. So I'm telling you, this minus sign is going to screw people up every time. So I do these two things, f of 1 plus h and f of 1 on the side, so that what I'm plugging in here is already simplified. Okay, f of 1 is the easy one. How do you find f of 1? Plug 1 in for x. 3 times 1 plus 1. 3 plus 1 is 4. Square root of 4 makes 2. Okay, this guy's going to be a 2. All right, how do you find f of 1 plus h? Plug in 1 plus h, same way. So instead of plugging in 1 there, you're going to plug in 1 plus h. Okay, so let's see, 3 times 1 plus 3 times h gives me 3 plus h plus 1. So this is square root of 4 plus h. You see that? 3 plus 1 makes 4 plus h. Square root of 4 plus h minus 2. Ah, no, I was wrong. How come no one fixed me? 3 times 1, 3 times h. That should be 3 h's. 4 plus 3h. 4 plus 3h. I got to distribute that 3 here and here. So that's a 3h right there. Okay, how do you find the limit? Plug it in. Okay, if I plug in 0 in the top, I get 4. Square root 4 is 2 minus 2 makes 0 over 0. Done. What are my 3 choices if I get 0 over 0? Factor, rationalize, combine fractions. Which one should I use? Rationalize. How do I rationalize this guy? I have to multiply by something. Yeah, what am I going to multiply by? It's going to have a square root in it. Yep. No. Plus 2. Yeah, I got to change this guy to a plus 2 instead of a minus 2. Square root of 4 plus 3h plus 2. Square root of 4 plus 3h plus 2. So when you rationalize a square root, you change the sign in between the two terms. If it's positive, you make it negative. If it's negative, you make it positive. Because the square root should go away now. Okay, so when I do that multiplication in the numerator, the square root should go away. So to do this multiplication in the numerator, I'm not going to do any multiplication in the denominator. I'm going to leave it just like it is. Because my goal is to make this h go away, right? My goal is to make that h go away. Because that h is what gave that 0 in the denominator and caused me the bad feels, right? That h gave me that 0 in the denominator, made things explode. Okay, so I'm going to try to do this multiplication up here. To do this multiplication, I have to do square root 4 plus 3h minus 2 times square root 4 plus 3h plus 2. So I'm going to multiply these two terms together. Then I'm going to multiply these two terms together. Then I'm going to multiply these two terms together. And then I'm going to multiply these two terms together. Okay, so I'm going to FOIL it out, do like a big old distributive. When I do the pink ones, square root 4 plus 3h times square root 4 plus 3h, what do you get? 4 plus 3h, good. When I do the pink ones, I get 4 plus 3h. Okay, now I'm going to do the green ones. I have square root 4 plus 3h plus times 2. So that's going to be 2 square roots of 4 plus 3h. Now I'm doing the blue ones. And that's the same thing except negative, which is what I hoped for because now the square roots are going to go away, right? Okay, then I'm going to do the yellow. So I have yellow is negative 2 times positive 2 minus 4. Okay, let me, this was the yellow. This was the green one. This was the pink one. No, they traded spots. I think my colors traded spots or something. Pink was the first one. Blue was this one. And yellow was that one. Okay, that was fun. All right, what are we gonna do in the numerator? Combine like terms. Yeah, this guy here and this guy here are exactly the same, but they have the opposite sign, right? Those two things in the middle are exactly the same with the opposite sign. So those two things in the middle cross out. Does anybody else cross out? A 4. So they have a -4 here and a +4 over here at the beginning. So they cross out as well. So in the numerator, what I have left is 3h. And in the denominator, I have h square root 4 plus 3h plus 2. Okay, what can I do now? Cancel the h's. Yeah, I have 1h in the numerator. I have 1h in the denominator. Cancel those away. That's good news. That's nice because once the h is gone, then all that bad stuff shouldn't happen anymore. Okay, what shall I do now? Plug in 0 for h, right? Notice that I wrote that word limit every single time. I wrote that word limit every single time so that when I got here, I would remember that I'm not done. I have not yet taken a limit. I did a lot of algebra, but I didn't do any calculus yet. Now I'm going to do some calculus, and I'm going to take h equals 0 and plug it in and see what happens. So when I plug 0 in here, I get 3 over 2 plus 2, 3/4. Pretty close to what we estimated, right? What did I estimate, like 4/5? 3/4 is pretty close. All of that to tell me that the slope of the tangent line to the function square root 3x plus 1 at x equals 1 is approximately 3/4. Okay. That's a lot of work, right? Luckily, eventually we won't have to do all that work. We'll learn some rules. Okay, this thing right here, this guy right here is called the difference quotient. This guy right there is called the difference quotient. There is in D2L a whole worksheet. Let me show it to you. In D2L, if you go to this week's content, we're in module 3. If you go to module 3, there's a whole worksheet, a boot camp on finding the difference quotient. And so it helps you, it practices, this is the answer key, but it practices finding the difference quotient. It shows you how to find the difference quotient for a bunch of different kinds of functions, okay? So it sort of builds it up, which is how I normally do it. And then it has you do the finding it and simplifying. So I suggest that if that algebra was a struggle, that you go practice some of these difference quotient things. Because what we're going to do on Wednesday needs that difference quotient. That's the only option we have for what happens on Wednesday. You can't use the other formula on Wednesday. You have to use the x plus h to a plus h formula. Okay, so that's under module 3 at the top. It says difference quotient. There's also a boot camp on find equations of a line. So if you struggled with finding the equation of a line, then that's there. Okay. Share back here again. Okay, so today you have 2 quizzes to do if you haven't done them yet. Yes. Okay, 2 quizzes to do. Go do them now. Don't forget that Gradescope one. That time limit includes uploading. I had 2 people this morning who ran out of time, so don't do that, okay? All right, I'll see you guys Wednesday.